In a previous video entitled The Geometric Structure of Atoms using the golden ratio, we previously briefly looked at this geometric shape which represents the shape of a hydrogen atom. Inside we can see the proton in red there as a little dodecahedron. We're just going to take a look at that little red dodecahedron. So what if a proton is a dodecahedron? There are many subatomic particles inside a proton: quarks, antiquarks, gluons, and various boson particles. So let's start with a proton. If it is a dodecahedron, it has 12 sides. So this shape can easily be split into 3 quarks. Of course, a proton is made up of 2 up quarks and 1 down quark. Now what holds these quarks together is gluons. So let's take one of these quarks away and have a look at the world of gluons. Now inside the proton is a stellated icosahedron. Now the stellations of the icosahedron are the anticolors of our quarks, and so they literally glue everything together. Of course, gluons are not the shape of the stellations of the icosahedron as shown here. Rather, the stellations of the icosahedron represent the region of space inside a proton where the gluons might exist. Now let's take the red and blue quarks away. So here we can see the stellated icosahedron broken up into 3 anticolors. These attract the quarks and glue everything together. When we learn more about gluons, we learn that there are actually 8 gluon colors. However, all 8 gluon colors are encased in these 3 anticolors. So in order to see all 8 colors of gluons, we would need to look inside the stellations of the stellated icosahedron. But before we do, it is interesting to note that there is a theoretical particle called a glue ball. Could this be what a glue ball looks like? So let's open up this glue ball and see what's inside. Here we can see the stellations of our glue ball opened up and flattened out. But now let's turn it over so that we can have a look and see what it looks like inside. So inside of our stellations, here we can see the 8 gluon colors. Again, this is not what gluons look like, but rather it represents the area of space that the 8 gluon colors might occupy. But what about the icosahedron in the middle? Let's close our glue ball up again. Here's our glue ball again, enclosed. But now let's remove 14 of the stellations. So here we can see the icosahedron in the middle. Now, could this icosahedron represent the antiproton? Of course, an antiproton is made up of 2 anti-up quarks and 1 anti-down quark. But let's take the remaining stellations away completely. So now we can see the full shape of our icosahedron. Now, an icosahedron is made up of 20 equilateral triangles. So how do you split a 20-sided figure evenly into 3? Well, fortunately, a triangle has 3 sides and can easily be split into 3 to make up our 3 antiquarks that you see here. But what might exist inside of our antiproton? Of course, a stellated dodecahedron, and the dodecahedron neatly fits inside of an icosahedron. Could this be the area of space where our boson particles exist? Possibly. So what if a proton was a dodecahedron? What we've talked about here today is very totally theoretical, but interesting. The reality is that subatomic particles are so very small that at this stage we cannot be certain of their exact shape or construction. So think of this video as theoretical conjecture over the possibilities, because we should always keep asking questions.